Today we're going to look at chemical equilibrium. Something we have not discussed with our chemical reactions is that some reactions are reversible. Let's take a look at the following decomposition reaction. Here we have, maybe we don't. Here we have carbonic acid, which is found in pop. This is also something that is a process in our bloodstream to get rid of carbon dioxide. The carbonic acid will decompose into carbon dioxide and water, okay? But then the carbon dioxide and water can react to form carbonic acid. When they manufacture pop, they pump carbon dioxide into the syrup. Well, there's water in the syrup, so the carbon dioxide and the water react and form carbonic acid in the pop. When you open the can of pop, then the carbonic acid decomposes into carbon dioxide, your fizzy, and water, which is why if you leave the pop alone for a long time, it will go flat, okay? And then it tastes watered down. This process also occurs in our bloodstream for us to get rid of carbon dioxide. The carbon dioxide waste is carried in our blood as in the form of carbonic acid, and then the carbon dioxide is released through our lungs. Anyway, when this process is occurring forward and backward at the same rate, we say that the system is in chemical equilibrium. This is the state in which both reactants and products are present in concentrations which have no further tendency to change with time. We call this a dynamic equilibrium because although it doesn't appear that there's any change in the reactants or products, they're being formed at the same rate. This is very important, okay? And the very next section is going to show you a video clip, hopefully, of this using water as a demonstration. You don't need to copy this slide down. This is in your book in chapter 17, I believe. And what ends up happening is this is a graphic way of explaining chemical equilibrium to you. At the beginning of at time 0, we have 0 products and we have all reactants. And as we start reacting, as this reaction moves forward, we start making some products, okay? And it keeps coming down, and then we've got more products. And then at some point here, we have less products or reactants than we do products. This system in particular is said to be in equilibrium, where we have more products than we do reactants. Okay, so the system's favoring the product side for whatever reason. And notice that the slope ends up being 0. So even though the reaction is going forward and backward, the overall concentration of our reactants and products remains the same. There is a principle called Le Chatelier's principle. And what this principle does is it helps us to predict the behavior of a system that's in equilibrium when changes occur to its reaction conditions. We consider this to be a stress on the system. This can be the amount in terms of concentration of our reactants or products. One of them gets changed, whether we pull product out of the system because that's what we're looking for, so then the system shifts forward even more, or we add more reactants or take away reactants to slow the system down. If pressure or temperature are related and involved in the reaction, say a reaction needs to occur at a particular temperature, and we change that temperature, we can shift it toward the products or toward the reactants as well. Finally, the amount of catalyst, if it's present, can also be changed. If we take away catalyst, then the reaction is going to go in the reverse, and it's going to want to go back to the reactants because at some point you'll run out of the catalyst. If you increase the catalyst amount, then the reaction will continue to pump toward the product side. Make sure you copy all of this down. Here are some diagrams that help explain Le Chatelier's principle. So I'm going to, let's see here. Let's take a look at the system in equilibrium, okay? we have the yellow element reacting with a purple-blue compound to form purple, yellow, and blue. And if you look here, we've got a complete system in equilibrium, okay? The energy has peaked and has come down, and our amounts are constant. Now, if we shift this over, I want you to look at the amounts. When we stress the system by increasing our BC, that's this guy, BC, okay? We increase more of it. Look what happens. We've increased more, but look what happens to our products. Our products have increased compared to here, okay? And our reactant, A, the yellow, has decreased because we're making more products. So if we're making more products, then the free yellow elements are gone. That's Le Chatelier's principle. If we stress the system, we'll shift it. So by stressing the system and adding more reactant, we've shifted to more product. Here is another example, stressing by increasing the temperature. So we haven't touched the reactants or the products at all. However, we've increased the temperature of the system. When that happens, again, now there's no increase in our reactants, but there's an increase in our products, and our reactants have come down because this reaction is driven forward by the increase of temperature.